To start with, we need to acknowledge the traditional owners of this country and recognise their stewardship of this country for over 40,000 years before European invasion. As you know, our speaker tonight is Stuart McKenzie, who's a Hobart-based architect. He'll be talking mostly about cross-laminated timber and how that works in a passive house, meeting the exacting standards of this. I think that's about it. So over to you, Stuart.
Thanks, Anne. I appreciate the introduction, and good evening, everybody. Victorians, Tasmanians, looks like we've got people from all over Australia and some from overseas. So thanks for tuning in. I'd like to say that I'm very grateful to be here. I've been a Renew member and a subscriber to the magazine for many years, and it's a privilege to be able to talk to you all. This is a topic that I've been involved with for quite some time, the topic of passive house construction. CLT more recently, we've done a couple of CLT builds in Tasmania now through our architecture practice, Next 50 Architects. And just broadly environmental issues is something that I'm also very much interested in. So what I like to do to set the scene, I think it's a bit strange to talk about any topic without putting it in context. So I'd like to put it into a very zoomed out 10,000 foot broad view so that we can kind of put this topic in context. So let's move right into that. So we are living in the 6th mass extinction. It's been referred to as the Holocene or the Anthropocene extinction. And that means that the background extinction rate, the normal extinction rate, is exceeded significantly. And the estimates range from 100 to 10,000 times the background extinction rate. And that's how we know scientifically that we're in the middle of an extinction event. And this is caused by human activity on this planet. Here are the other 5 extinction events. Sorry for the doom and gloom, but I think it's important to kind of set this context. I'm going to do it fairly briefly. So about 440 million years ago, 85% of all species were made extinct during that event. And these were pretty, you can see kind of the diagrammatic way that the Earth looked in these different eras. 145 million years ago was the 5th, 76% of all species were made extinct. So these are pretty massive events. And the fact that we're in the middle of one is worrying, to say the least. And the climate breakdown is just a part of that, a major part of it. But nonetheless, it's also related to human activity. So putting Australia in that context, has one of the worst recent extinction records of any continent. So more than 100 species of vertebrates since first people arrived here over 50,000 years ago. I'd like to say, this is a quote, but I'd like to say that I suspect that the majority of the extinction that's happened on the Australian continent would have happened since colonialist times. I'm pretty sure that Indigenous people would have had much more respect for the land than we do. So now we're looking at 300 animal and 1,000 plant species that are considered threatened with imminent extinction. So what are we going to do about all of this? This is where we're sort of starting to get towards the end of the context discussion. I've been interested in, and this is only one aspect of the discussion, but I think this is a fascinating book. Edited by Paul Hawken. If you haven't seen this before, I recommend looking at it. Drawdown, as the title suggests, is a very comprehensive plan. And it's not a plan about theoretical ideas of what would happen if we did this, or if some new magic technology was invented that allowed us to use clean coal or something. This is just about scientific data on things that we can do right now that we're able to do, and then it's ranked 1 to 80 in order of efficacy. And this is important for context because it puts what we do with buildings and efficiency in overall context. So I've made a quick snapshot of the first top 10, and then some other interesting ones where they sort of fit in the 1 to 80. And then these are kind of the category totals. So let's just have a quick look at these because it's quite interesting. So the number 1 individual item is just management of refrigerants. It sounds really boring, it hardly gets any media attention, but it's a very significant reduction. These reductions, by the way, are based on the current data, assuming that we continue, for example, with wind turbines, if we continue to roll wind turbines out at the current rate, allowing some idea of moderate scaling, by 2050, we build onshore wind turbines at a similar rate and start to increase scale, we'll save 84.6 gigatons by 2050. Refrigerant management, because it's such a huge global warming potential, 89. Then there's reduction of food waste, eating a plant-rich diet, so minimizing animal products in your diet. I've lumped into food the stopping cutting down tropical forests because it has a lot to do with the animal agriculture industry. So the reason for just talking about all of these is that food by itself, in all of the categories combined, is a massive part of our impact as human beings, which makes sense. We all live, we all breathe, we all eat multiple times a day, and it causes this enormous impact on the planet. Then energy use. Again, this is an aggregate over everything from 1 to 80. Obviously, wind turbines pretty high up there. Solar farms pretty high up there, makes into the top 10. Rooftop solar makes it into the top 10. Then this is an interesting one that most people don't talk about, doesn't come up in the discussion. Education of women and girls, which is basically about providing education in developing countries, has such a massive impact. And so it's surprising. Obviously, if there is sufficient education for women and girls, they may choose to have less children. This can have a massive impact on the outcome of our future as a civilization. So I'm not suggesting for a second that this necessarily is higher overall than the impact of buildings. This is just looking at some of the impacts in context of this book, Drawdown. So then when we come down to about number 31, we get insulation. And there's nothing really in there for passive house buildings or zero energy buildings specifically. It's kind of split into data sets. There's a bit on LED lighting, heat pumps. I've just dropped other things in there that people think about, like airplanes. It's pretty far down the list. Electric vehicles, reasonably far down the list. These are relatively small impacts. So that kind of gives a bit of context for buildings. But what we have to do is we have to now look at how these are all interconnected. So we all live in buildings, most of us. We all eat our food in buildings. We refrigerate our food in buildings. We all use energy in buildings, hence energy in total. The energy use around the world is very significantly from buildings. So just because of this information doesn't mean we can count buildings out. But those buildings that are referred to in this projection for what might happen in the future relates to new builds, which are a very small percentage of buildings in the world. The buildings that are going to impact our survival and our future on the planet are really the existing buildings. So we probably need to be having a bigger discussion, which is not the purpose of tonight's talk, but around retrofitting. So why should we prefabricate? Why shouldn't we just build as normal? Obviously, ever since Henry Ford and the idea of a production line, we've learned about the assembly line process, the benefits that come from that, like quality assurance, automation, accuracy, and efficiency. So the cookie cutter suburbs we see around the world and in Australia, this image is not from Australia, but you get the picture. These are actually an assembly line in some ways. So the whole of Australian kind of suburban building systems are set up as systems. Brick veneer buildings are very much the product of an industrialized system. They don't happen inside a factory, they're not strictly prefabrication, but they are systems of a predetermined way of doing things. They're done en masse for efficiency, hence everything looks the same, which I'm not suggesting is a good thing. But it is something that we need to be aware of when we're talking about prefabrication and the impacts that can have. I guess the other obvious analogy would be like the car industry. We don't get to have bespoke vehicles, we get to select from a range that a given manufacturer would make. So if we're moving away from standard building practices and talking about CLT and passive house buildings, one of the first questions is, why timber? Why would we build in aluminium or some other material? So there are some health impacts with timber. The obvious benefits, or maybe not obvious to everyone, but timber being a renewable resource, potentially carbon neutral if the timber that is used is reforested. There is still going to be an impact, we know that. And it's certainly not out of the question that CLT has an impact on the environment because of topsoil health and deforestation. But however, that said, most of the timber used in CLT that I'm aware of is spruce from managed forests, different types of pine that are common in European managed forests. So beyond that, in terms of health, we know that workers are less stressed and more productive. Students learn better, patients heal faster, and people are generally happier and calmer in indoor areas which contain wooden elements. So this is from a recent study. It was republished in Vogue Living. Timber has the ability to lower your heart rate, to minimize the stress response in students and workers. And it also aids in speeding recovery time after surgery. So pretty interesting health effects. And I think Passive House ties in with this quite well because there are health benefits from building a passive house, which I'm going to touch on quite a few of them tonight. So why CLT, why passive house? I'm going to use New Zealand as a little bit of a case study. There's a resource here which is excellent called Passive House for New Zealand, The Warm Healthy Homes We Need by Jason Quinn. It's a 2019 publication. New Zealand had a problem that it identified quite some time ago, which, among other things, costs 6.16 billion a year in public and private costs because of respiratory illnesses. Respiratory illnesses caused by what was referred to as the leaky building syndrome, just generally poor quality building. So New Zealand's been a bit of a test case. The homes are cold, so the average New Zealand home is 16 degrees C during winter, which is the temperature at which respiratory illness increases, or the risk of it. At less than 12 degrees, there's a high risk of stroke and heart attacks. Now, in this study, 12 degrees and less was found inside bedrooms, typically. The WHO, the World Health Organization guidelines call for an indoor temperature of at least 18 to 21 Celsius, particularly if babies and elderly are resident. And this is a mind-blowing statistic. 1/3 of New Zealand homes contain mold. A lot of these problems are addressed by Passive House and Passive House systems, and I'll go into that as we go through. I just wanted people to be aware that Australia may be lagging behind in this, but we're facing this same pandemic, if you like, for want of a better word, of moving into, as we increase our building standards, as we increase mandatory and energy efficiency standards, increase insulation and the efficiency of doors and windows, we will also increase condensation risk and therefore the risk of mold, unless it is dealt with by our building codes, which is only just starting to happen and in a very sort of ad hoc way. So jumping back to CLT for a second, what is it? It's a timber panel. You can imagine it a bit like prefabricated concrete or precast concrete in the way that you make panels off-site and then they're lifted into place with a crane. And I'll show some examples of that. But why it's cross-laminated, so you can see in this image there's the timber on the outside and the inside of this panel, which are called lamellas, run vertically. And then that's the end grain of the middle lamella, which is running horizontally, hence cross-laminated. Because timber can shrink along its longitudinal axis along the grain, by cross-laminating timber, you increase its dimensional stability. So once this is cut to size by a CNC machine, it will tend to stay close to that size that it's cut. So that's one of the benefits. It's a bit of a diagram here showing the same sort of thing. So this particular panel is a 5-layer CLT panel with doweling or finger joining between the timber, which is all done in an automated fashion. Pretty much, if you visit a CLT factory, as I've done in the XLAM factory here in Albury-Wodonga on the mainland, which is pretty much a brand new facility, the timber goes in one end of the factory as a pack of pine, and it's processed almost entirely in an automated way and comes out as a fully cut and finished CLT panel at the other end without a human hand touching it. It's very fast, it's very efficient. Talk about that a bit later. So here are some of the advantages. Dimensionally stable, as I just mentioned. It has the potential to span both ways, a bit like concrete. Because it's one big solid panel, it has excellent bracing properties, so resistance to racking loads from wind and structural forces. It has very fast assembly on site. Again, I'll talk about the speeds in a minute. Very high accuracy, an excellent earthquake and storm resistance in the structure itself, and relatively easy to achieve a high level of thermal performance and airtightness performance, which is important for Passivhaus. We'll talk about that in a bit more as we go on. Here is an example of a test bed. So this is a 7-story CLT building. This whole bed that it's sitting on is a testing bed for simulating earthquakes. So this will shake and then they'll test the building with sensors. They put dummies and furniture and things inside to see how it performs. You can see it's a joint test between Italy and Japan. Both have high seismic issues. CLT has been used as emergency housing in Italy after the big earthquakes that happened recently. It's incredibly good in earthquake conditions. There's some resources at the end. I'll mention Paolo from Wood Solutions, who is a bit of an Italian CLT engineer and guru who we have access to in Australia, and has done a lot of work in this area. So that's one of the exciting places that CLT can be advantageous. So obviously in a setting like New Zealand, it's also super useful. Not so much an issue in Australia, but just worth noting about the material itself. So that's a little bit about CLT. Let's flick back to Passivhaus. I'm going to go back and forth a little bit as we go through, just so you can see kind of the relation between the two things. So there's a bit of an overview of what Passivhaus is. And I note from the poll at the beginning, I'm pretty much preaching to the choir tonight. So a lot of people at Passivhaus either have some knowledge of Passivhaus or Passivhaus professionals. I apologise if I'm going over basics that people already know, but I'm trying to appeal to the widest audience possible. And I'm not going to make any assumptions with that. So Passivhaus started in 1991. Today there are over 60,000 homes that have been built to the Passivhaus standard, and many that have attempted to over and above that are not certified. So it's not a brand new idea. This is something that's been tried and tested. It's been tested in a lot of different climates. And essentially what it comes down to Using modelling and climate data and careful design, there's a requirement to reduce the heating and cooling total energy demand to 15 kilowatt hours for every metre squared of the building internal per year. So I'll talk about what that means in a minute in terms of actual heating costs, but it's very low. Somewhere between 80 and 90% less heating and cooling energy than a normal building. And it achieves that through exceptionally high levels of insulation, shown here in the diagram with the yellow zone. So essentially we've got a complete surround of insulation underneath the slab, up the slab edge, around the walls, throughout the roof, with very well insulated windows, frames and glazing, windows and doors. So any of the openings use a high performance system. Thermal bridge free, so the construction will mitigate heat loss through conductive pathways, so elements that might be in a wall, like a stud, for example, which is a very minor form of a thermal bridge. You can have much worse forms of thermal bridges, like just uncontrolled openings with metal components, for example, which are more conductive. So it takes that into consideration, whereas something like the Energy Star rating system, which is mandatory in Australia, does not take into account the thermal bridge-free design. It doesn't even really look at it. Another important aspect of Passivhaus is airtight building envelopes. And that really is about draft control. So it means that when you ventilate the building, you do so through a controlled way when you decide to, which is either through opening a door or window or using your HRV system. And that brings me to the last point. So ventilation control is an important one. I'll come back to, or air tightness. I'll come back to that in a bit more detail because there's soon more information later in the presentation. During winter and during even in peak summer as well, an HRV system or a heat recovery ventilation system is often a feature of passive houses. It's not actually a requirement, but you'll tend to find them in most passive houses. It means that in the middle of winter when it's freezing outside, warm inside, you can bring in fresh air, which is preheated by the heat exchanger core using a very small amount of energy to provide fresh air to the living spaces and to extract stale air from bathrooms and places like that. And it uses a very low amount of energy, and it means that you don't have to open windows in the middle of winter. So it adds a lot to the energy efficiency. Another image of basically the same thing, diagrammatically showing the air intake and the stale air exhaust, the heat exchanger unit, supplying warm, fresh air, extracting from the kitchen, from the bathrooms, stale air. So just going over some myths. Australia is too warm and Passivhaus is overkill for our climate. So this is a myth for a number of reasons. Firstly, Passivhaus is customized to the local climate. So the climate data for the area that you are building in, the specific area that you're building in, the specific altitude is optimized and it's designed into the building at the design stage. So it's not a one size fits all system. A building in the middle of Siberia is going to have much more energy requirements to meet Passivhaus, thicker insulation, higher performance windows, more of a reliance on thermal separation of the floor slab, and all these details will be different in a house in Siberia to a house in Victoria or Canberra. They'll share some things in common, but they'll still be different. And then the number one source of household energy use in all the states of Australia is heating and cooling. So this is actually from Renew, from May 2019. And this is ACT, New South Wales, Northern Territory, Queensland, South Australia, Tas, Vic, WA, and the top blue component is space conditioning, so heating and cooling. And for the cooler states, the majority of this energy is actually heating energy. So by far in the cooler states, it outweighs all other forms of energy use. So purple is water heating, appliances at the bottom. So in some places like Northern Territory and Queensland, obviously appliances actually form the highest part, which is interesting. But just the point being that there's sort of a myth that Australia is this super warm country and you don't need to heat your buildings. Well, obviously you do from this. So a building that reduces heating significantly, like a passive house, is going to make a big difference. So I'm going to move into the case study. This is the first passive house we did. Passive house with CLT, or using passive house principles. It's not certified, but we went through the same process, which is a bit different to the case study I'm going to look at tonight. I only show this because I think you learn things from doing things previously and then trying to incorporate the learning from this first example into the next build. So this is the interior of a passive house made from CLT in Hobart. Not a certified passive house, but built on those principles. This is the exterior. It's got metal cladding. Now I'm going to dive into the case study for tonight. So this is a shot from a couple of weeks ago with the build. I'm going to show you what it actually looks like finished in a CAD model. So this is the design intent. This is the northern elevation we're looking at here. So it's got a fair amount of glazing on the north. And what you'll see there is a bit of an eave overhang that's kind of optimized for Tasmania to cut out that high level summer sun. Same on the bottom, so it's actually a box built into the cladding. So typical passive solar design features. Because of the block running north-south, it's actually a long building and its long axis so obviously some of these back rooms don't get the direct northern sun. So to try and get a bit more light deeper into the building, we've got a fairly big roof light. And I'll show you internally what's going on so you get a bit more of an idea of the building. So there's a void here over the living space, living dining space. There's a little entry lobby here. I'll go to the downstairs in a second. Coming up the stairs, there's a second living upstairs, which is kind of a sewing craft room. There's a master bedroom here, which has an ensuite underneath this little loft area and a walk-in robe. And there are two kids' bedrooms that have built-in bunk beds that are made in the CLT. So I haven't showed all the joinery in this system, but one of the reasons I'm showing you this part of the model is there's a mechanical room up here with the HRV system pre-located in it. And you can see all of these little openings in the CLT, which are predetermined. So there's predetermined downlight holes, there's predetermined openings for the CLT, for the HRV. These are cut in the factory on the CNC machines. They're very accurate, and it means that we don't have to do hardly any processing on site. So I'm just going to switch off the ceiling zone. So shows you a bathroom, walk-in robe. So there's 3 bedrooms up here with the ensuite. Switch off that first floor so we can see what's going on downstairs. And downstairs we have the open plan kitchen, living, dining. There's a second living space, 4th bedroom, which is for an elderly parent, and the main bathroom, laundry, pantry area, and then the stairs up. Now, that's a fairly large house, but it's sort of similar to the Australian average of about 230 square meters. I think this is a bit bigger than that. It's about 280. Don't quote me on the exact square meterage. I'll have to check that. But I want to show you, that was really just to give you an idea of the building, what it looks like, how the spaces are arranged, so that when you see some of the images, it'll make a little bit more sense what we've achieved with the CLT. So that gives you a bit of an overview of the building. So this is designed and then modelled in the Passivhaus planning package, as well as the energy rating software. A lot of the things are optimised in that process. So we look at things like we needed to add a sun protect coating to the glass in this roof, because we're getting a little bit of overheating when we were modelling it in the summer. And Passivhaus allows for some overheating, but it's to a limited degree. So there are the sort of feedback loops that you get from doing the modelling early in the build. Some of that feedback that comes through the Passivhaus planning package modelling is much more specific than what you get from the energy rating software feedback. You do get some useful things out of the energy rating process, the star rating process that's mandatory, but that also depends a little bit on your consultant. The consultant we have is very experienced and is able to interrogate that star rating model quite in quite a useful way. So now that's the finished building. The CLT skeleton underneath it is basically like this. So as we design the building, each panel has a sequence number so that we know in what order those panels go up. That's all planned from the beginning. The lifting points are planned into the panel. Things like recesses for these purlins or cross purlins. A lot of detail goes into this phase, including, as I was mentioning, the integration of CLT HRV holes for the HRV system. So that's an extract point. Obviously, we're going to have a lot of heat in the top of the void space here. Just the heat's going to rise to the top of the space. It's going to be extracted from this point and then distributed more evenly through the house. The other thing that's done in the CLT model is outlets, so electrical points, some holes for plumbing and a few other details, so that when this turns up to site, the building, once it's erected to this point, the structure is complete. Also, all of the internal linings are complete. So with the exception of the floor finishes, but the ceilings are CLT, the wall finishes are CLT, and there's no more work to be done then other than painting. So I'm going to show you a video from site. So this was after about 6 or 7 days, I believe. I'll have to double check with Justin, but it was about 6 or 7 days to complete the installation of all the CLT panels. So this was before the roof went on. This is one of the large wall panels. It's the full length of the building, and you can see it here being lowered into position. So all of the panels on a CLT project are lifted into place by crane. The weight of a timber panel like that is about the quarter of the weight of concrete, so you get away with a much smaller crane, but it's still a crane-dependent process. But the reality is that means this wall goes into place pretty quickly and efficiently and accurately. Once it's fixed off, it's pretty much millimetre perfect. And then the only thing that's required to make it airtight is taping of the external joints. You can see in this video there's some taping already done on these external joints wherever the CLT is connected. I'll talk about the air tightness a bit more in a second. That's that panel in position. So I'm going to show you another very brief section of a video, just watching a CLT. This is a CLT module that's being put together in a prefabricated prefabrication facility. So they're going to put, this is not done on site. There's the CLT, sort of a diagrammatic explanation of CLT, the different lamellas in the different directions. They're putting screws into the panels, which is how they're fixed together. This is from a 500 bedroom hotel in a pretty harsh climate in Germany. That was not just made in CLT, but in the factory, but then the pods were pretty much completely finished, so that when they were taken to site, they were already fitted out. A little bit different to what we're doing, but I just wanted to show you that because it gives you an idea of, that's then putting in electrical cables, gives you an idea of pretty much how quickly it goes together. They've done the same thing that we had with predetermined electrical points and fixture points. So going back to our case study then, you can see now an image of the building as it's under construction. It's still under construction at the moment, but I want to show you some interesting shots later into how it's developed. That's inside that void space. This is the pop-out box here I was talking about that provides the shading. These are German triple glazed windows. So part of that Passivhaus building envelope is to have very energy efficient windows and doors. And these are timber frame with an aluminium cladding on the exterior, triple glaze with a very good U value, and a triple glazed skylight. But you can see if the CLT even includes the rafters, it's all housed in, all of that work is done. So you have a very finished building very quickly. This is one of the upstairs bedroom areas. So this is actually the master bedroom, and this is a little loft up here. You can see the hole there for the HRV system. You can also see in the background through in the other room, there is a balustrade which already has some slots cut in. This is all done on the CNC machine as well, done in CLT. And you can see the brackets that tie it down. I'll show you how these are hidden a bit later on. This is Justin O'Connor, the builder in the void looking down. This is a slab on ground. I'll show you the details of that later. It's completely thermally isolated slab, dark in color and polished so that it absorbs the heat from the sun. So just very quickly, I'm going to do a very slight digression onto the climate zone. So you see these dark blue and light blue areas all through southeastern Australia and Tasmania. These are all cool, temperate, mild temperate zones which require, it's even fairly far up into New South Wales. These are all areas where we benefit from Passivhaus, and Passivhaus can also be used in hot climates. So they build them in the Middle East. So just because it's a hot climate doesn't mean you can't benefit from a thermally controlled envelope. In Hobart, yeah, during winter, overnight temperatures can drop as low as 3. We're in a microclimate in Ridgeway, so we're up at about 350 meters, I think. So that takes out another 2 degrees off, so you're sort of getting overnight temperatures of close to 0. And depending on microclimates, you'll have areas where you'll definitely get frost. So I just want to talk a little bit more about a review of the standard and what we're talking about, and then I'll go into the specifics. So one of the important things here, air tightness, 0.6 air changes per hour, pressurized at 50 pascals. I'm going to go into that a little bit more. I'm definitely anticipating that there'll be some questions about Passivhaus costs. So this is just one reference I found, 5 to 10% more to build than a conventional equivalent, which is quickly offset by the dramatically lower running costs. We're finding in an architectural build, this building, for example, that we're looking at in the case study, is actually not more expensive than an equivalent architectural building that would be bespoke, designed by an architect, built in the same city with none of the provisions of Passivhaus. So in some cases it's cheaper because a high spec build with high finishes and things will be more expensive in this building. So part of what offsets cost, obviously, is that you keep that heating below the magic 15 kilowatt hours per meter squared per annum. So these are your losses, these are your gains. They need to be, if they equal out, then you're doing pretty well. So you get a balance. So you're going to get a significant amount of loss just through the building envelope. You're going to get a very large amount of losses through the windows and doors. And then you're going to get some ventilation losses. And these are mitigated a bit by the use of a heat recovery ventilation system, as I mentioned. And then, so that's your losses. In your gains, you're going to have some gains from heating, but you're going to keep those below that limit. And I'll talk about some anecdotal evidence with heating now, actually. So the house that I live in is designed to the Passivhaus standard. It doesn't face the right way because of the peculiarities of the site. And if I work out my house at 15 kilowatt hours per meter squared per annum, it comes up to allowing me running a small 1.8 kilowatt heater, just a little, like tiny little fan heater. That would allow me to run that heater for almost 2,000 hours in a year. Well, anecdotally, I would say I would run it between 100 and 200 hours maximum. So it's significantly less than this 15 kilowatt hour requirement, and it's still a very comfortable house. And that's about $50 of heating energy for a whole year, which is nothing. Internal gains will vary on how occupied the building is. The house we're in is probably pretty large for 2 people, so we don't have a huge amount of internal gains. And solar gains, as I said, we're not optimally oriented, but we still do get some pretty good afternoon solar gains, and you can feel it anytime the sun is out. It almost instantly feels comfortable in the house. Plenty of thermal mass to keep that balanced out. So you can see this example here. 10 tea lights or the body heat of 4 people can keep a 20 square meter Passivhaus room, a 20 square meter Passivhaus room warm in the middle of winter in extremely cold climates. I just use the icon of a thermos to kind of make that point. It's very efficient. So we're going to talk a little bit more about the Passivhaus planning package, PHPP. So whenever you want to design a Passivhaus, you have to use this modeling software, and you input all of the specifics, the climate specifics, the shape and geometry of the building, and then all of the specifics around the glazing installation and the values of the insulation, etc. It's very detailed. And then it gives you some interactive data where you can play with, for example, increasing or decreasing your shading to optimize the heating and cooling loads. You can look at playing with your ventilation rates. There's all sorts of things that you can do. But this is how we locally adapt to the specific site and climate that we're designing for. So looking at air tightness as one of those key ways of achieving this great thermal efficiency. This is an example of a pressure test or a blower door test. We have to achieve 0.6 or around about half an air change per hour at 50 pascals. So less than 0.6 or 0.6 and less meets the Passivhaus standard. To give you an example of what that means comparatively, an average house in Australia, if it's really well built and a new build, it might get 5 air changes per hour, and there are plenty that have 20 air changes and above. The general standard of air tightness in Australia is shockingly bad. It's just not really considered. In the pressure, so this is a pressure test that you see here. So essentially they open a door, through the front door or wherever, insert this blower door test mechanism, which is pretty much just canvas on a frame with a fan that's calibrated to some pressure testing software and devices in the laptop to give you a readout. And I'll show you the result that we got with our CLT house. So this is the N50 refers to the 50 pascals. It's both pressurized and depressurized, and then there's a whole heap of readings that have to happen till that is calculated. It's based on the volume of the air in the house, and there's a lot of detail that goes into setting up this. So we achieved 0.17, which is a very, very airtight building. When I say we, I really mean Justin O'Connor, the builder. With his experience in Passivhaus, he's had prior experience. He's a certified Passivhaus tradesperson and consultant. He knows a lot about the field. He was very nervous about this particular test because he'd never done a CLT house before, but he'd done other buildings. And so he, with blower door tests and with air tightness, air leakage control layers. And CLT doesn't have a typical air leakage control layer, which I'll talk about in a sec. I've been talking for about 50 minutes. I'm going to be wrapping this up pretty soon and opening up to a panel discussion, but I'm just going to try and get a little bit more detail in the end of this discussion so we understand some of these points in a bit more detail. So right after this test was completed, this was a preliminary test. This was without a roof or cladding on it. It's just the CLT up. It was wrapped and taped. The windows were installed and taped. And then he achieved this phenomenal preliminary result. And then right after achieving that result, he found two small holes about the size of about the diameter of your thumb, which the electrician had left to outside air. So once they're plugged, this will be among one of the tightest buildings in Australia, so which means that it will be very, very energy efficient. How is that achieved? So there are some details here. I'm going to start from the bottom and just go around the building. This is the slab on ground. It's quite thick because there's no footing. There's some special slab prep. So the dispersive soil was removed, FCR was packed down and tested for compactness and made very flat. And then we've got extruded polystyrene foam, a very high density type of, well, not a high density, but a high strength foam rated to 300 kPa, so it can support a slab and building load. So there's literally no ties anywhere to the ground. This slab is completely encased in a thermally efficient insulation. It's 50 mil under, and I think we actually used 50 mil PIR on the edge in the end because it had a high enough R value. So this grey is the slab. The yellow is the insulation zone that continues up and around. This is the CLT layer here. So this is the 80 mil CLT wall. And these are the tie-down brackets, and these are all completely taped. All these brackets are taped over. This junction of the slab to wall is all taped from the outside. There are some images of that later, which I'll show you. And then this is the insulation zone. There's some surface cavity in here, but it's also in the insulation zone. So we've got about 135 mil of insulation with a zone where surfaces can run and still have at least 90 mil of continuous insulation. There's a membrane, which is a weather tightness layer, a rear ventilation cavity, batten, and then cladding. So that's the foot of the building, if you like. As we go up the wall, that insulation layer continues up. We've got our CLT, which is pre-cut to the sizes for these renovation profile triple glazed windows, which have this rebate. So they just fit straight into the hole with the little air tightness tape that was put right here before the window was fitted. They're fixed from the outside with this little red tape flap is a proclimber tape, wraps continuously into the membrane. So once this is fitted in the hole, it's completely finished from the inside. There's no more finishing to do on the reveal. So we've got a, technically speaking, there's a small thermal bridge through here, which has been modeled in the Passivhaus planning package, but it's still timber, so still pretty well insulated. And there's some expanding foam tapes in here that provide some insulation at these weak points. So moving up, here is an internal, that's the first floor level. This is important for some images I'll show. We're almost at the end now. That's the actual finished floor, which is a hardwood floor. There's a service cavity. This is the upper wall. The brackets are hidden on the inside. The insulation is continuous. We've got the top of the window. Moving up. This is the junction with the roof. So thick insulation on the roof. I think we had R6 in here. And I think you get about, on average, you get at the very least, in the weakest point, you get R2.6 in the wall, and you've got about 0.9 R value in the CLT. And then if you have it all entirely insulated, where there are no surfaces, you're getting close to R3 here and about 0.9 there. So pretty high R values all around. Just the CLT alone in the roof at that thickness is over R1, and then you've got your R6, so you've got at least an R7 roof. Rear ventilation cavities again, continuous membrane all the way around, and a little flap into the gutter, which is added later, which is a little bit non-typical in Australian detailing. And then this is the ridge just showing how the insulation continues over. So we used I-joists on top of the CLT just to create a 250 or 240 cavity, the R6 insulation. So I'm going to wrap up with a couple of little more images of building, and so it'll make sense of some of these details in a visual sense. But why do we do this? It's because if you do it with the appropriate insulation, thermal breaks, high quality windows, the internal surface area, the internal surfaces have a much higher temperature than a normal building. In fact, in a passive house, if the air is 20 degrees inside, none of the surfaces will be more than 4 degrees less than that 20 degrees. Whereas in a typical standard sort of build, you'll have a cold window, you'll have drafts created by that, increased air leakage rates, so you're going to have radiant losses and convection losses and all sorts of losses that you don't have in a more controlled environment. And all this warmth that's been kept inside in winter is being recycled effectively by the HRV system. So here's an image of the upper level. You can see the CLT floor below. That forms the ceiling of the level below. And then we have this cavity. So this duct you see here is actually an HRV duct. This particular HRV system has a very small heat pump, which only uses 1 kilowatt of input energy to have about an output of about 4 kilowatts of heating energy. It can also provide a little bit of cooling. And that's a very tiny top up, very, very efficient for a large house like this. Like that's the smallest of heaters. You probably get a hairdryer that's about the same wattage as that. You can see also our cabling is running under the floor, and then it runs up into the PowerPoint here that's already finished. So what's pretty amazing about some of these images, what you have to appreciate, and this is a very key difference between this method of building and normal building. This is a house with no cladding and no roof on right now, but yet it's completely finished on the walls, finished around the windows, no more work to do. PowerPoint's already in and wired, surfaces are going in. This is what it looks like on the roof at this exact same day. So it's got its wrap on. There's the rear ventilation cavity created by these longitudinal battens. Proclimber wrap with the special tapes underneath, NADOC tape underneath the counter battens. All taped and continuous into the wall membrane. So what it means is one crew can be working on the outside. So you could have a roofer on site and a cladding crew outside working on the scaffolding. Meanwhile, inside, things are progressing. So this is the floor going down in the master bedroom. There's an HRV duct. It's insulated to avoid condensation when you provide that little bit of extra heating. So this is a supply duct. Hardwood floor going down. At the same time, bathrooms are fully tiled already. Everything's solid too. Everywhere you go, you've got a solid substrate. So you can fix joinery wherever you want. It's super flexible. This is joinery going in. This is just an example of that skylight. It's been flashed and made watertight, ready for the roofer to do the final installation of the roof cladding. This is a bit of a grey, rainy day in Tassie, and you've got a building that's weather tight without actually having any cladding or roofing on, so that guys can work inside. So even on a grey day, you get a lot of natural light. This will have battening, as you saw probably in the model, to cover these are the different openings from the kids' bedrooms and the bunk beds. So with all of this attention to detail and thermally efficient building, it means that you can have a building where it's 21 Celsius inside and minus 14 outside, and there'll be a nice even temperature distribution in the rooms. And there'll be no condensation on the inside. All the condensation will be on the outside. So this is an example in Hobart. It's actually one of Justin's previous houses to build a dripping condensation on double glazing with a non-thermally broken aluminium frame. And this will lead to mold and then respiratory illness, all those things that we know about from the New Zealand case studies. And you'll get uneven temperatures. So the glass, this double glazed panel will be cold, and you'll get this unevenness, you'll feel draftiness and cold. That will not happen in a passive house. It goes right into the detail of, even if you look at this, is quite interesting. So, and this is pretty much my last slide actually before we go to questions. We're just bang on an hour. An aluminium spacer on double glazing. And look at the outside temperature, minus 10, 20 C inside. So that's the case for all these different windows. This is just showing you how important detail is in the passive house system. So with an aluminium spacer, you get condensate. And you can see the actual conductivity value of that edge spacer. So we're getting down to a detail of talking about the spacer that separates double glazing and how to specify that. Stainless steel spacers in a triple glazed window still creates a thermal bridge through here, and you get condensation. That's a very efficient window frame. Timber with aluminium cladding, a good triple glazed window with a poor performing edge spacer. Even a slightly better one and still getting mold. Then when you actually do what's called a Swiss spacer or an insulated edge spacer, which has a much better conductivity value, lower being better R value effectively, you don't get any mold, any condensation. So these are the sort of details that are going to be considered in a passive house. So I might just finish just with a few acknowledgements. And these are useful for when this video goes online so that people can contact the different people involved in the project. So Justin O'Connor was the builder and still is. And highly recommend him. He's just been amazing and does an incredible job, super quality conscious, very knowledgeable, and extremely, just a great planner. And considering it was his first build with CLT, he just did an incredible job. People that are interested in mass timber construction for different projects, there's a free service called Wood Solutions, and Paolo, I mentioned him earlier, he's the Italian CLT engineer. You can speak to him at woodsolutions.com.au. They provide like free advice when you're interested in doing a mass timber building, like a CLT construction. In Tassie, we use Paul Clayway from Building Evaluate to do the energy ratings, the star ratings. This building had over a 9-star rating, but I guess that's not really important other than giving us an indication of performance. What was really important is the modeling. But Paul also does blower door tests and has a thermal imaging camera and has a broad range of knowledge and expertise. So we really value his input in the design and refinement of the design. We've worked with Stephen Cole now from Integral Engineers a couple of times because he has some knowledge of the Stora Enso CLT system. And so it's really good to work with people who are familiar with the systems. The CLT in this particular case study was supplied by Stora Enso, and the contact in Melbourne is Erki. We've worked with Erki on the previous build, and we've already got some on the drawing board for the next ones as well. An interesting aside to the whole CLT process, we used an ethical mortgage broker, AB Finance, and Andy helped broker a deal with Bank Australia to help finance the CLT project because it has a unique cash flow, which is that you have to pay more upfront in the early stage because not only are you doing a base stage and building a slab on site, you're also paying a deposit for a project that's being built in a factory in Europe, and banks typically don't want to fund things like that. So this project was more than just a case study for efficient design. It was also a case study for trying to get banks on board with the whole process of doing things differently, which banks typically aren't set up to do. So good on Andy, the crew from AB Finance and Bank Australia for backing this project. It simply wouldn't have been possible without that support. And then finally, last but not least, Passivhaus planning package, or the Passivhaus modelling. Torquil Canning has been doing work on that for the certification. And that's super useful feedback. We're still refining how a plan for ventilation and whatnot to just get overheating a little bit under control, which is about the only area that we've got an issue with at the moment, which is quite minor. Yeah, so I dare say I've skipped over some things in the process of trying to smash this out in an hour, but there was a lot in there, so I'm going to close now and thank you again for listening, and look forward to having a bit of a panel discussion at the end and a Q&A.
Right, the first question he has from Rick. He wants to know if CLT can be used for flooring.
Yeah, that's a good question. On our first project, because the clients really wanted to, we used CLT for flooring. It's not recommended as a flooring product because the pine is quite soft, so it would perform a bit like a Baltic pine floor. And it also means if you use that CLT for a floor, you don't have a space for your service cavity. So you'd end up suspending a ceiling or something underneath the CLT. So you're reinventing a system that's tried and tested in Europe many, many times over. So we learnt that lesson from the first one. And so the second one, we did a hardwood floor with the service cavity underneath the way the Europeans do it. And to be honest, it was a much better system than our first crack at doing it. So that's the short answer to that.
Okay, these are all sorts of different orders. Okay, you've probably already answered this one. For Passivhaus design, when you say very high insulation, what sort of ratings are you talking about? I think you've fairly well answered that.
Yeah, I think the important point there is the insulation is designed appropriately at using the Passivhaus planning package modeling to optimize it. So you don't need to go overboard, you just do what is required to get you to the level that you want to get to. So, I mean, obviously you can exceed even the Passivhaus standard. So once your model shows that your heating demand and cooling demand are under 15 kilowatt hours per meter squared per annum, then you've met the standard, but you could then go further. So in some case studies, I've seen people get that right down to 3 kilowatt hours per meter squared per annum or whatever, and they're probably doing that through a combination of things. So the short answer is you model to find out what insulation level you need.
Okay, Paul is asking, is there any fundamental barrier to operating an accredited Passivhaus in a more traditional passive solar way if you have sufficient mass? Can you have the best of both worlds?
Sorry, Anne, would you mind just rereading that question?
Well, I suppose the question is, most of us have come from the traditional passive solar thing where you're maximising solar gain and then having quite a lot of thermal mass to balancing that out. And the question is basically, is there any real barrier to operating an going for accredited passive house and also incorporating the traditional passive solar elements?
No, there's no barrier to that. In fact, a lot of passive houses already do that. The difference between a passive house and a traditional passive solar house is pretty significant though. And that is that even if you don't have the optimal solar gain, it will still perform. And the problem with traditional passive passive solar that we're starting to understand now is one, it's not really modeled, so you don't have really good knowledge of how it's going to perform, and it's dependent on the occupant and the occupant's use patterns, because you don't have things like HRV systems to balance out. You have to open windows in the middle of winter. There's all kinds of drawbacks to it. So I guess if you wanted to make it simple, you take traditional passive solar principles, and you build on them, and we get all the benefits of the passive house system on top of that. So they certainly build on each other, but passive solar in a traditional sense is really just an older-fashioned way of, or one of the earlier stages in our evolution of understanding what makes an energy-efficient building. So I would say that really the modern version of traditional passive solar is a passive house, because it's doing all of those things and more.
Okay, this is a rather long one from Paul. I'll try and summarise it a bit. He's saying that the massive timber in CLT isn't working anywhere near its structural capacity. Have you looked at the economic and environmental cost of the timber resource in a low-rise CLT home and compared these costs to compared costs to using basically an insulated serviced, basically cavity framing, more conventional approach if you're using fast-grown plantation wood? So you've got more on-site labour payments rather than capital-intensive labour saving in a factory, particularly when it's an overseas factory.
Yeah, it's a good question. There's probably a lot of different ways to approach this one and how you would answer it. The short answer is I don't know the direct numbers off the top of my head to compare the two. I do think so I'm not in this talk in any way saying CLT is the answer. I'm just really presenting it, trying to show you some of its advantages, and I didn't really talk much about its cons. So I would say one of the cons of CLT is that it's so timber intensive. That said, in a multi-residential or a more high-rise setup, higher density living, I think you'd get more benefit out of it per square metre than you do in a low-rise residential setting. So there may be better uses than just standalone houses. That said, it's a heck of a lot better than using precast concrete in terms of the carbon intensiveness of it. So you're right, and thermal efficiency of it, the safety. There's so many reasons to use it from that perspective. The benefits you get doing a prefabricated system just don't come with timber. Timber still has to be stick framing or balloon framing is an idea that's been around from the 1800s. It's a very old-fashioned way to build. It's not efficient in terms of labour on site and weather conditions, and you've still got to line it with something. And what is that lining? It's plaster, and plaster's a pretty low-quality material in my opinion. A timber building made from CLT is going to outlast a traditional building, I would say, by a country mile. So just in terms of the stability, the bracing, the resistance to storm events, all the things we're going to be seeing more and more in the future, I would put my money on a CLT building outlasting a conventional build. So quality over time is a big thing. I don't think it'll ever, in the short term, on a small scale, beat out balloon or stick framing on cost. But like anything with prefabrication, you have to have an economy of scale, and we just don't have that yet. But once we had an economy of scale on a whole system of where the construction industry is just behind CLT and not behind stick framing, then we could probably see some economies. The energy intensiveness of all of that timber versus stick framing is probably a really good point, but then you have to not just look at the stick frame, you have to look at the lining, the bracing, all the other things, the insulation you've got to add. All of that has embodied energy and an environmental impact as well. So it would be a pretty complicated question to answer properly. Yeah.
Okay, Matthew wants to know whether there's a minimum distance between the HRV intake and the exhaust outlets.
Good question. There is, there's a minimum distance, and I can't remember what it is off the top of my head, but I think it's the best to check for sure. You want to talk to Joel Seagren at Fantech that supplies Zendair. In this particular house, we used a Zendair system, and we do have the inlets at, I mean, actually what I can do, I'm just going to very quickly check it in the model because that was correct. So just bear with me 2 seconds. So in our current design, we have exactly 1900 center to center. And I'm going to say that that's close to the minimum. Obviously, the further apart they are and at different heights and whatnot, then you get a better result. In other houses we've done with HRV systems, they're much further apart. So yeah, please just confirm that with the manufacturer of whichever system you specify. Obviously, Zendair is not the only system, but we just tend to stick with them because they're a very good quality system.
Okay.
Look, Joel Seagren's actually just not jumped on and said 1.5 meters sounds great, Stu. So that was the Joel I was mentioning. So thank you, Joel, for that.
Good. Sarah wants to know whether you could use CLT for second story additions on existing buildings. What would some of the considerations be?
Basically, I don't see why not. You just have to have sufficient support and structure underneath it. So yeah, I don't see why not.
Okay. What energy rating software did you use for the early modelling? I think it was Natters, wasn't it?
We used, so Paul Claywait used Accurate for the star rating, and we used PHPP for the Passivhaus planning stuff. So we used them both simultaneously to get different feedback.
Okay, whoops, where are we going? Brett wants to know if you used other timber products in the design along with CLT, LVL, GLT, NLT, all these other acronyms.
Yeah, to some extent. So the CLT is the main frame and structure, and even the beams are actually CLT as well. Externally to that, we've got, excuse me, we've got battens and counter battens, which is all just MGP pine. We've got the timber eye joists with the, I think, I'm not sure which eye joists we use, whether they had an OSB or a ply web, just to create a cavity for the ceiling insulation. So yeah, a lot of timber products, timber door panels, obviously a Taz oak floor upstairs, and some pine battening. So a lot of timber products, I would say.
Rosemary wants to know what type of taping you used.
All ProClimber products, so ProClimber tape, ProClimber membranes. From personal experience, the ProClimber tapes, they stick incredibly well, and they are both, the tapes and the membranes are a whole system that's tested for vapor permeability. So they allow essentially the condensation to make its way through the wall system and vent out the rear ventilation cavity. They don't allow moisture in, but they allow vapor out. So that's a really important decision for your condensation control. So really good question. And then you also want somebody, ideally, who's a Passivhaus certified tradesperson who's done training in the application of these tapes, because you literally have to, it's not just about sticking them on, but they have special tools to smooth them and make sure that they're stuck really well. And there's lots of little tricks to it. So if you saw the taping on this building, unfortunately I didn't have any good pictures of it that I should add when I do this talk again. The taping was immaculate on this job. I've never seen anything like it. It was incredible, and it was worthy of a framed piece of art by itself. So.
Okay, and this one follows on from that. Rhiannon wants to know where you put the vapor permeable membrane the National Construction Code now requires in Zone 7.
Was that the question of where did we put it?
Yeah, where do you put the vapor permeable membrane?
We put
Inside
it
or outside? Outside, I assume.
So yeah, it's interesting because the CLT building doesn't have a double membrane. So if we're doing a Passivhaus stick build, we have a double membrane. So we have a air leakage control layer, which is Proclimate and Tello on the inside of the stud. And then on the outside of the stud, we'll have the vapor permeable membrane, and they have different layers of different levels of vapor permeability to encourage a direction for the condensation to flow. And that external one on the outside of the stud then has a batten on the outside of that before the cladding. So you get a little cavity behind the cladding and the membrane. So in this case, the CLT is the air leakage control layer. So we have no internal membrane. And the external vapor permeable membrane goes on the outside of the insulation batten zone, which is on the outside of the CLT. But it still has its rear ventilation cavity after that membrane before you get to the cladding. So it's a bit of a long-winded explanation, but it's in the details. This will get posted as a YouTube video by Renew, and so you can actually go back and look at those details once that's posted, and you'll see all of that in there, because it's a dotted line shown in the details on the outside of the yellow insulation zone.
Okay, Robin wants to know, well, how does the cost per square compare to other building techniques? Yeah, I think you sort of vaguely said not so easy to work out, but...
Yeah, in this particular case, we were under the cost that I've seen other architectural builds done in the state by architects that have done none of the Passivhaus stuff. So normally you'd expect it to cost more. In this case, it did not cost more than a standard architectural build. Now you might say, well, what's an architectural build per square metre? And I would say probably somewhere between 3,500 and 4,000 a square metre. But we typically see architectural builds go like 4,500 a square metre for a high spec building. Now that might seem high to people that are buying a Metricon or a Wilson home or something. That's probably, I don't know, sub 2,000 a square metre or something for a piece of junk building. But we don't see anything. If we come in under 4,000 a square metre for any type of architectural build, we usually know that we're kind of in the ballpark for the market. So be interested. I think it'll vary. Tassie's probably slightly higher price than maybe other parts of the mainland. I don't really know. So don't have that much experience in mainland construction. So, but I believe there is a bit of a difference down here.
Okay, this is an interesting one. Inga wants to know if there's a way to shade the huge skylights in summer.
That's a good one. So the skylights are working for us and against us in this building, and they create a little bit of overheating in summer. But what we have on that triple glazed skylight, there's something called a sun protect coating, which is a clear coating, or mostly clear. You can't really tell that it's there. It kind of opal, I guess it's like polarizing sunglasses. It looks a little bit different if you really examine it next to a normal glass. And that reduces the solar heat gain coefficient to 0.25. So that's half the amount of solar heat gain that you get through a normal triple glazed window. So that has to be tested in. We're still getting a little bit too much overheating in this building, but again, anecdotally, and you can't really rely on anecdotes, but the Passivhaus buildings that, well, the one that I'm living in now, on the day we had in Tassie, which was one of the record temperatures, super high outside temperature, over 40 degrees, we did a purge of the thermal mass the night before, because we saw the weather forecast and knew the heat wave was coming, and the house stayed cool all the way through the day, even though we have suboptimal orientation, and I don't have any of the special glass in my house. So being up in Ridgeway, which is a high altitude, if the clients or the owners of the house kind of know that they're expecting a few days of really hot weather, they can purge the thermal mass at night, which simply means opening up all your windows at night and getting all that heat out in the cooler evening air. That'll cool the thermal mass, and then you just shut everything down the next day. We'd still benefit from probably a little bit of external blind shading or something on some of the eastern windows, just minimally. So yeah, what I'm really interested with this one is that the modelling shows a little bit of overheating in summer, but not a huge amount. Tasmanians generally don't use cooling, but we've got some cooling capacity in the heat pump on this HOV system. I don't think it's enough to keep up with that little bit on the really extremely hot days. They're just so few and far between. I'm looking forward to a post-occupancy evaluation to see whether the occupants ever feel too hot. I think, you know, there's lots of ways to cool down that are also to do with occupant habits and stuff. In this building, you can retreat to rooms that are further away from the direct sun. There's all sorts of things you can do. The heat recovery ventilation system will help because it will go into a summer bypass mode automatically, and you can increase the flow rate, which just means you'll get more airflow. You can open different windows for cross ventilation. There's quite a few things you can do. And yeah, so it's a long way around of answering, yeah, skylights are tricky, especially in one of the original designs, that skylight was on the other side, which was more west facing, and that was cooking the house. So we moved it to the eastern side. We still get the same amount of sort of daylight from the sun, from the sky, but we reduced our overheating load. So that was partly from feedback from the modelling.
Okay, Paul's got rather a long one here. He's concerned about the importing of the CLT from Europe when it's possibly come from logged, poorly managed native forests. Why did you choose that over the X-Lam from Albury Wodonga, which is plantation radiata pine, or the CLTP Tasmania, fabricating CLT in Wyndham, Tasmania from Eucalyptus nitens, it's otherwise going off as wood chip. You know, why did you choose the European version versus Australian versus Tasmanian?
Great question, and there's a good answer to that. So firstly, the Tasmanian plant was not up and running when we did this build. I believe it may have just started operation, but I don't have any details on it. I think it's a really good thing to buy local, and if we can use Eucalyptus nitens for the core of the CLT, that's great. There's a few things related to X-Lam. I think X-Lam is a super interesting, super high quality factory. I really like the product. We both, my offsider and myself, went to the factory and looked at X-Lam. We got them to price this job. X-Lam has a couple of things which are quite different in the way they operate to Stora Enso, and this is really important distinction. So X-Lam's kind of set itself up to do big, fairly simple panels. So for, I guess, large scale commercial jobs, it's not set up with a small CNC machine to do fiddly little detailed jobs like residential, like this building is a good example of a fairly detailed build. So Stora Enso actually has two different CNC machines. There's a smaller one. They also have a kind of a beam processing facility, which X-Lam doesn't have. So when Xlam quoted this, all the fiddly parts, they actually quoted to do manually. So the quote was significantly higher than the Stora Enso quote. So even though we really wanted to use Xlam because we wanted to support the Australian company that was just, well, German owned, but Australian based, the timber company Hein owns Xlam. So we're still ultimately a German facility. Well, the Stora Enso comes from Austria. There's another factor to this. So that was all the kind of on the surface things. Really liked the idea of Xlam. You could do bigger panels, bring them down on semi-trailers, come across on the boat to Tasmania. And all of that still costs a fair bit of money, that transport down, because the BAS rate tax, as we call it in Tassie. So if we could make it locally in Tasmania, we'd be better off. The other thing about Stora Enso is they have a lot of expertise and support and information that they supply to us as designers, and that we'd also spent some time skilling up by doing the previous job in Stora. So we've sort of gone down that rabbit hole a little bit, and it found that to be really useful. Xlam is still really just kind of getting set up here, and so I'm not trying to badmouth Xlam in any way. I think what they do is great. I want to see them get a bigger and bigger market share, and the more CLT, the merrier from my perspective. I can't really comment on because I don't know off the top of my head where the timber comes from Stora Enso, but I could definitely find that out. I think that's an important question. I don't think it is FSC certified, but we certainly aren't FSC certified in Australia either. So radiata pine plantations aren't necessarily any better than plantation pine in Europe. I think that the quality of the timber from Europe is better. So it has less knots. It is got better moisture control. So I would put my money on if you see Stora Enso side by side to Xlam, Stora Enso is a much better looking product. So look, aesthetically, it's better. Environmentally, good question. Don't know. I would like to do some more research on that so I know the answer.
Okay. Matthew wants to know how much the double void over the living area impacts the performance of the HRV. Is there a maximum percentage of floor area ratio?
Basically, the HRV system is sized to the air volume in the house. So Joel, when he's looking at it, or when Justin's looking at it down here, they're reviewing the floor plans, they work out the volume of the house, and then they size the machine accordingly. So they just take into account that void volume. So it's pretty simple calculation, basically. But we've done a few houses with HRV systems that have voids or high ceilings. And the benefit of the void is that you can put that extract point up high and get that all that heat that's collected up the top and redistribute it throughout the house. So you get that more even warmth spread throughout rather than hot pockets and cold pockets.
Okay. Did you have to do anything extra for acoustic insulation between the floors? There didn't appear to be anything obvious there when they're putting the floor down. But...
Yeah, good question. No, we didn't do anything for acoustic separation. So just a single residence. So there's some, I guess there's some mass in the CLT floor, which is 140 mil solid and thick. And then you've got the batten space and the hardwood floor. So it will be interesting to see how the residents find it.
They clearly haven't got small children.
Well, the small children are, yeah, they're not that small, and they're upstairs too. So everybody's upstairs. No one's running. The only people that will be on top of anyone, the grandma might be downstairs and the parents will be upstairs. So it'll be a good one for feedback. There are products made by Rotherblast who make CLT accessories that provide kind of acoustic membrane breaks and things like that. And if you would, obviously, if you're doing a multi-residential, you put a lot more thought into that. It's not really something that we put much effort into, but thanks for bringing it up because it's probably something that should be thought about. Also, just noticed on the chat that Tyson from Xlam popped up. G'day, Tyson. He just said that Hein Timber, Xlam Australia is an Australian-owned and operated company. So that's good to know. And somebody else has said that someone's just popped up a documentation that, in fact, Stuart Enzo is FSC certified. So Forest Stewardship Council, or FSC certification, is a very thorough chain of custody certification. It's very hard to get. There's very few companies in Australia that have it. So I think that's, that answers that question, that the Stuart Enzo product from an environmental perspective has a very high rating. So again, I'm not trying to play one off against the other. I think both have pros and cons, and they're both good products. So you can make your own informed choice about which way you want to go. There are, just for the record, there are some examples of pretty big X-Land projects down here in Tassie, which I've seen. So yeah.
Okay, this one suggesting that it's effectively a reverse veneer construction with a stud frame exterior to external cladding. Or is the external stud frame still constructed on site? Basically, it isn't a stud frame, is it? It's more just battens.
Yeah, exactly right. So it's just battens screwed to the CLT. And then, so there's vertical battens to create a, let me just see, I think I've got a photo I can quickly pull up. I'll just have to share a screen again. Actually, I won't bother, but I can do that. I can send that later unless people really want to see it. But essentially, there's no stud frame that's created. We did do that on the first CLT house we did, and it was overkill. So you can just screw the batten directly to, in this case, there's a double batten. There's a vertical batten screwed directly to the CLT, and then there is a horizontal batten that supports the cladding. That is screwed horizontally using long batten screws all the way through into the CLT.
You've pretty well covered that the freight and shipping costs are a problem coming into Tasmania. Okay, one on the bathroom and so on. Are the tiles fixed straight to the panel? There'd have to be a waterproof membrane, wouldn't there?
That's correct. There's a couple of things actually that I think that we nail fixed 4.5 or 6 mil fibre cement sheet, and then the waterproof membrane was applied, and then the tiles. I guess the benefit of the CLT in this case is that when it's installed accurately, like as Justin did, you get a very solid, very plumb wall that's very straight, and so you're not worried about like bowed studs and planing things and trying to muck around to straighten your wall, which is traditional carpentry requires a lot of that mucking around, and that just didn't really exist. I mean, Justin's tiler is also excellent, and the tiling in the building looks incredible. So, but yeah, it's definitely still got to apply those waterproof membranes and the fibre cement sheet substrate.
Okay, now Peter's in a great spot. He's in a high bushfire area and with a flood overlay. So he's concerned about what bow rating you can achieve, and can it be built on high stumps without a slab? I'd have thought Ridgeway was in a reasonable bushfire rating as well, but
yeah, it's actually not too bad. I think our site was only 12.5, bow 12.5, which is not that high. The short answer is the CLT and the Passivhaus systems can kind of be built into any environment. So, but a lot of the bushfire provisions affect, for example, the windows, it affects the glazing, toughened glass in higher bushfire zones of specific thicknesses. So it makes your windows more expensive, but that's going to be the case no matter what. And it affects some of the detailing around, eaves and gutters and rear ventilation cavities having to have metal mesh for ember protection. So generally speaking, it doesn't really make any difference. For this type of system, it can adapt to all of those different requirements. Can it be up on poles? I don't see why not. If you just Google CLT buildings, there's a huge diversity of shapes and forms, and you can do a lot of stuff with that.
Okay, Talene loves the design, but is interested to know how you could get the roof windows in without the modelling showing a high percentage of overheating. Is this thanks to the Tassie climate? Isn't it a case that the modelling basically doesn't really consider overheating?
No, modelling does consider overheating in a lot of detail. So in the Passivhaus planning package, it looks quite carefully at overheating. So you just design for it. How can we get away with that much skylight? Yeah, it probably is partly to do with the Tassie climate and the altitude, but we still have, I think Hobart has second highest sunshine hours of any capital city in Australia, so we still have a lot of sunny days. So that you just have to model it. It's too high a risk thing to not model and just to guess. And the thermal values of that glass are very carefully considered. So high U value plus the low the sun protect coating. So that's all really important stuff. And look, if you could integrate into it a really good external automated blind that wasn't going to break the budget and wasn't going to cause a maintenance issue down the track, then yeah, that's probably not a bad consideration either.
Okay, Lawrence wants to know if you know of any life cycle assessment information for any CLT house in Australia.
No, I don't.
Right.
Just thinking where would be a good resource. Yeah, I don't know. If I come across any, I'll definitely forward that to Renew just to consider, but I don't know of any.
Okay, Brett wants to know whether the foundation on the Ridgeway house was designed to AS 2870 or AS 3600, because he understands that the edges of foundations require a minimum of 25% edge thickening.
The edge thickening is integrated into the overall depth of the slab. So that, I think it's a 200 mil thick slab, which is thicker than probably a lot of edge thickening anyway. So if you think of the whole slab as thickened in this particular case, then that's kind of how that was achieved. And there was quite a bit of negotiation back and forth with the builder, myself, and the engineer to get to where we got to which is, looks very simple, but initially it had all kinds of thickenings and different thicknesses and different types of supports. So it was quite a complicated site because of the dispersive soil. So there were some complexities to work around there, but the outcome was really good and simple in the end. So yeah, presumably the engineer designed to the standards that you mentioned. So I wouldn't really know, not being a structural engineer. So we rely on them to do their bit.
Okay, Vince is worried about Vox with all that glue. Is it a problem?
Yeah, good question. Yeah, good question. So CLT, several issues here, I guess, to bring up. An HRV system, which is running all the time, is constantly refreshing the air. So a lot of VOCs are taken out. So you're going to still have VOCs in your tile adhesives and your grouts and your joinery and many things, your furniture, your computers, everything has VOCs in it that you install, the paint finishes on the CLT. So between the lamellas of the CLT, they use modified polyurethane glue, which I understand has a relatively low VOC after it's gone off. It's not a perfect material. Look, if you had the money and you were really wanting to not do glue, there is something called dowel laminating timber. So they laminate with dowels, and there's no glue. And there's a construction standard around it. It's been done for many years in Europe. So there are ways around it. But I can tell you anecdotally that when you walk in the building, there's no sort of glue smell or new building smell, and that's without the HRV system running. But then after the painters were in, you could smell their finishes, and the joinery has a bit of a smell. So the HRV system will certainly make a huge difference clearing that out. And the reports on air quality and oxygenation and health of occupants with HRV systems all suggest that that is a really healthy aspect of the Passivhaus system. And because it's only a 40 watt fan, and even if you're just on your off-grid solar system, you can afford to run it all the time. And it's a very robust thing. Fans can run for a very, very long time with very little maintenance. So obviously if that was broken down for any reason, you've got the option to open windows and cross ventilate.
Okay, Kimberly lives in a very cold, leaky home in New Zealand. And she's wondering whether there's an option to retrofit CLT to help make the house more insulated and make it safer, or would it be a viable option, I guess? So you're retrofitting CLT as an insulation product.
Thanks for the question. Yeah, I'd say it's not really viable for that. It's more of a new build type of product. For retrofits, to make your building more airtight, it's pretty challenging. There's lots of ways to do it, but it kind of just depends on budget. And I don't know if you have heritage overlays and whether you start from the inside out or the outside in. Well, there's probably the ideal way is to take off all the linings on the outside and re-insulate and put membranes on and make them all airtight and then reclad it. But that's a very expensive thing to do. But energy efficiency retrofits, there's a lot of books on it. There's some excellent books by Burkhauser in the Detail series that you can look at. There's a whole book dedicated to energy efficiency retrofits. And Europe has a pretty massive wealth of knowledge on it, because in Germany it's actually required that whenever you do a renovation of any kind or a retrofit to a house, you must bring it up to the new standard. So there have been many different ways that that's been dealt with in Germany. So hence there's a lot of information on it. So I recommend looking at those sources or finding a designer that has some experience in doing that. Yeah, but unfortunately, yes, CLT just probably wouldn't be an appropriate material for what you're talking about.
Okay, Kim's worried about logistics. What was the length of the longest wall panel you used, and is this greater than standard trucking length?
Short answer is not greater than standard trucking length or 40-foot container length. I think the longest was an 11.3 metre panel. I'll just double check in the model real quick. Yeah, that one you actually saw going in on the video was about 11.8 metres. Obviously, if it comes from store at Enzo, you're limited by container lengths and widths. So there was some constraints around that. So that's one of the cons of store at Enzo is you end up with more panels and more joints. Whereas with XLAM, you're only limited to your semi-trailer sizes. So XLAM could have probably done bigger panels that would have had less joints. So it's all depending on where you're coming from. But even with XLAM, you have to consider, are you going to do an extra wide load and therefore have to have an escort and all those kind of things. So you have to really plan all that stuff out. Store Enzo, in our experience, was just very good at planning all that, and they did all the logistics for us, including the delivery to site on the semis. So all we had to do was push the order button and then wait for it to show up and have a crane ready to unload it.
Okay, Jane and Kathy would like to know who makes suitable double glazed windows or triple glazed windows. That's a good question. Again, you want to get advice from a really well-qualified designer and energy rating consultant, whether that's someone doing the PHPP, because in your particular climate, you might only need double glazing with, let's say, a U value of 1.5, including frame 1.1, let's say, which is a pretty well-performing double glazed system. And then you would have an option to go to any supplier that can provide that U value. So depending on where you live, it would vary. So I know pretty much all the window suppliers in Tassie. There are quite a few double glazing companies that have thermally broken frames. There's a couple that do triple glazing. Same in Victoria. I'm not really sure further afield. Conflict of interest note. I sell triple glazing, and that's one of the hats that I wear. So I'm being careful not to mention my brand because I don't want to be here promoting my business. That's not the purpose of the talk. But if you pretty much Google triple glazing, double glazing, thermally broken frames. So your thermally broken frame options are basically PVC or thermally broken aluminium, which tends to be fairly expensive and high energy intensive in the production of them. And then you've got timber
windows and timber with aluminium clad. So there are a lot of companies that do it, and you really just have to search through and make sure that you compare apples to apples with the U values, the solar heat gain coefficients, all those specs. That's why I'm suggesting a third party that is not affiliated with a window company, like an energy rating person, that is often quite a good person to ask, because they can show you when they do the star rating, if you put double glazing from X company in your building, this is your heating load, or if you put it from Y company, this is going to be your heating load. So they can compare double to triple, and you can then compare the costs and figure out that extra heating cost over the 30 years you're going to live in the building or whatever. So the best way is to kind of do it systematically, compare the numbers and see how it all stacks up.
Kim wants to know how you do the wall to floor joints. You use self-tapping very long wood screws, skew nailed, or is there a bolt system of some sort?
If you're talking about the floor to wall in the upper story, there's just big angle brackets. So if you're talking about the first floor fixed down into the lower walls, we just use very long screws. So various companies, Rotherblast, Spax, Worth, a lot of them are European companies, make screws that are kind of designed for the CLT system. So the screws can go right up to 450 long. That's all specified by the engineer. So how many of those screws, how often they are, the diameter and the length. I don't think we used anything longer than 250 long screws in this build from memory. And then there are a lot of angle brackets, which are screwed with coach screws into the wall, and then with other coach screws down into the timber floor, or with anchor bolts down into the slab. So again, those fixings are all specified by your engineer. So really in the engineering package for CLT, there's some very detailed specs on fixings.
Okay, Francis is interior design students concerned about the VOC levels for CLT. Do you know what the levels are, and do they use formaldehyde in the glues these days?
So as I was mentioning earlier on that other question about VOCs, volatile organic compounds, it's a modified polyurethane glue, my understanding, in the Stora Enso product, which means it doesn't have any formaldehyde in it. That doesn't mean it doesn't have any VOCs. But again, VOCs tend to have a peak in a few days after they're applied in glues, and then they taper off and kind of diminish right down. Typically, not always. There are certain things called persistent VOCs, which are often not measured in our standards. But then the HRV system is venting out. So by the time you have moved into a building, a lot of the VOCs will have passed their peak of off-gassing, and the poor tradesmen that do the building will cop the majority of it. And then the HRV system will take over and do a lot of that venting. So the VOCs in a passive house with an HRV system will be much lower than any other type of building that I'm aware of, unless you specifically design to cut out or make all your products very low VOC. But even that it's a huge challenge. I've done a fair bit of work in this area. And just to give you an example, certain big name paint brands who will remain anonymous have figured out how to do, to add masking compounds to their paints and finishes, so that when they do the test, it picks up less VOCs than are actually present. So it's like a test. They're cheating the test in the same way that VW is cheating the test on emissions, and you don't get what you pay for. So it's a really big area. It's a massive rabbit hole to go down. I think it's really good to be thinking about VOCs. It's good to be thinking about reducing formaldehyde, like urea formaldehyde and some of those really high off-gassing things, even epoxies with bisphenol, carcinogens, all those kind of things if you're thinking about it. But, you know, as I said, it's a rabbit hole, and you're going into antimicrobial compounds and fire retardants that are in carpets and computers and all kinds of stuff. So it's a big, it goes to not just the building, but also what's the furniture and the appliances and
children's clothing.
Yeah, exactly. It goes into everything. Clothes we all wear. Often, you know, t-shirts got some sort of formaldehyde in the packaging. So it's like, It's crazy. We live in a very industrialized, toxic world, and it's a massive problem. It really needs probably a talk all by itself. But I'm not volunteering for that one. This is too big a topic.
Kim wants to know how the vertical runs of electrical cabling are accommodated.
Yeah, good question. Super interesting. In CLT, that's one of the things that Stora Enso does really well, because they have a very long horizontal drill. And if you design the panels in such a way, you can go about 1.8 meters into the panel from the edge. So that may be from the top down or from the bottom up, 1.8 meters at about 25 mil diameter. So effectively that's your conduit hole for your cable to run in. Yeah, so you do have to do a little bit of planning around where your fixtures and fittings, your switches and your power points are, but it didn't really prove to be too much of a challenge in this build. I think there was only one panel where we had to do a routed groove and then patch it with some timber later and sand it, so which is another way you can do it.
Okay, we've got two questions here that are fairly close and they're probably not going to be possible to answer. David wants to know what the CLT costing for the demo project was, and Damien would like to know what the final cost of the Ridgeway house is.
The final cost for the Ridgeway house is somewhere, I can't tell you the exact figure, but it's low to mid 800s. Yeah, for a fairly big house, 280 square meters or somewhere around that. I'd have to do the numbers again exactly. What was the first part of the question?
Oh, the CLT cost. So
basically the raw CLT cost for this project delivered, again, this is a bit of a guess, it's going to be close, was about 120,000, something like that.
Okay, Lynette wants to know how you finish the internal sides of the panels. Can you use a breathable oil?
Sure, you sure can use a breathable oil or a vapor permeable oil, if that's what you mean. Yeah, you can leave it unfinished if you don't mind marks. So you know, it's going to be pretty tough in most cases. Obviously, you wouldn't probably do that in an area where you're cooking and you've got a lot of potential grease or staining things. I think in this case, the owners have specified a clear finish in some panels and like a lime wash on others, and it's paintable, so you can use a range of different finishes depending on your VOC/natural requirements, whatever it is that you're trying to go for. So it's a timber substrate, so there's so many different finishes for timber that would be appropriate.
Okay, Peter wants to know what you see as the principal advantages of using CLT over passive house construction using air seal membranes and conventional frames. So basically CLT versus a well-sealed standard house.
Principal advantages would probably be, in my personal opinion, a much longer lasting, stronger structure that can withstand not only use and abuse internally with the impact resistance of the CLT finish, but you know, super high wind loads and storm issues and movement with any sort of differential movement in the ground. And so I think there's some longevity benefits. Obviously speed of construction, simultaneously being able to finish the inside and the outside. So there's a speed benefit. Reduced use of plastics. I mean, all the membranes are plastic. So I personally think timber is a better material than plastic, but I've got a bit of a bias there. I think there's also, I'm not pushing for CLT, as I said. I think it's an interesting material. I don't think it's the be all and the end all answer. I think there's different projects require different things. CLT at the moment is more expensive, for example, so a lot of people would be put off by that.
So the last question was, how was the glass in the triple glazed windows certified to Australian standard?
Good question. So essentially it was just specified to the Australian standard. So if it was required to be safety glass, then it was laminated, because there's no toughening requirement in this particular building because of the bushfire code. And yeah, that's basically it. Just making sure that you use the safety glass in the right areas. So you'll find that there are a lot of companies that import European glass, and as long as you're complying with the Australian standard from what you specify, then that's basically all you do.
Paul wants to know the brand of windows that we used, and do you have the FRSI values for the installation thermal bridges to the windows?
Torquil, who is doing the PHPP modelling, would be able to answer your question about the installation values. So that obviously varies with the different types of detailing that you use. The brand of windows in this Unilux windows, imported from Germany.
Might as well stay on windows for a bit. Can you explain the method of fixing the windows? Are they fixed solely from the exterior?
Yes, but they use an installation clip that's pre-mounted to the side of the window. And that installation clip is then screwed, it's basically a metal strap that has holes and slots in it, and that gets screwed through the CLT on the outside. And then the membranes cover all of that up.
Okay, there's one here about, and there's no ceiling cavity, so what do you do about lighting? Did you have recessed downlights?
Yes, so in the floor, the first floor, so the suspended floor, you recess both the downlights and other features like HRV, HRV extract points or distribution points. But then above that floor, above that ceiling, you have that false floor cavity of about 140 mil where you can run all your cabling and everything. So that's your void to run all of those things. And in the roof, they're also recessed, and then the cabling runs to the outside and inside the insulation zone outside the CLT. You run the various ducts and cables. So it's a little bit backwards to kind of how a normal building works. But.
Did you consider Gutex for insulation? I don't know what Gutex
Yeah, I
is.
think it's an excellent product. So for people who don't know, Gutex is a brand name for wood fiber board panels. They're used a lot in Europe. They're not easily available in Australia. I think they might be imported by a crowd in South Australia, maybe if I'm not wrong. Comparatively, they would have been very expensive for this build and would have blown our budget. I think it's an awesome material. Ecologically, it's probably one of the best insulation materials I know of, just made from wood fiber. I think there'd be an interesting case for how you get it certified through building surveyors and things here. That could be a challenge, but I'd love to see either that made in Australia or imported and used, and try to push people away from fiberglass bats and rock wool bats. It's a much, much better product ecologically, even from an installation point of view, because you can just basically fix it straight to the CLT and then put your counterbatten or your membrane and then your counterbatten on top, screw all the way through. And a lot of CLT construction, I wouldn't say a lot. I've spoken to Karl Zenkel, who is a professor at one of the universities in Germany, he's also an architect and a specialist in timber construction, and he tells me that wood fiber panels are not used that much in Germany either, because they're expensive in Germany, and so people tend to use foam and things more, which, you know, obviously foam's not that great, XPS and EPS. So yeah, good question. So there is a CLT. I'm sorry, I don't think it's a CLT project, but it's a Passivhaus in Australia. I've seen the YouTube video online that uses something like a Gutex panel, and yeah, I was really impressed to see someone doing that. It's great.
Okay, Tony's concerned, if you can't get crane access, is it possible to assemble smaller CLT panels on site with biscuit joints or some other type of joint, and what disadvantages would this bring, apart from time?
Yeah, apart from time and the number of joints, you can cut CLT panels obviously quite small, and you can, in smaller components, you can manhandle to a degree. You can Yeah, look, on a difficult site, you just have to assess it case by case. Like, one option with a difficult site is get a really big crane, and then you can reach a long way. Or if it's you can get small crawler cranes, or you can use an excavator if you're really clever with it as a small crane. So there's probably, you try to exhaust, I think, all automated options first, or heavy lifting devices first, before you try to go down that track. Because the CLT does have automated lap joints and things, and you could have more of them. Just be very time consuming, and you'd have a lot of visible joints inside. So I don't know, I think you just have to really try hard to avoid that if you could.
Okay, Steve says CLT can provide all the structural strengths. Well, can CLT provide all the structural strength for a multi-storey house without any other structural elements? You sort of showed that on the shaker table, but you didn't show how it performed.
Yeah, so that was a 7-story building. Lend-Lease, I think, did a, I was going to say 10-story. I think Lend-Lease in Australia, they've been doing CLT longer than most, and I think they've got plans for a very tall tower building in Melbourne. Going a little bit off memory, I think deemed to satisfy with a concrete plinth, or for the first level, I think you can go up to 25 metres in mass timber. And so I'm pretty sure that the Lend-Lease tower was about 10 stories. So typically 10, yeah, I think there's a Berlin building 13 stories, you know, these, and some in London. There's examples all over. Someone in Canada is trying to do one at 30 stories. Some of them don't do it entirely in CLT, but you can go up to those sort of 7, 8, 9, 10 stories purely in CLT. Sometimes they use like a concrete plinth for the first level. Sometimes they'll use a stair or elevator core in concrete to add some additional strength. But I think the one in London that I was looking at had a CLT elevator shaft as well. So I think fire standards permitting, that's where it becomes a little bit tricky. So that the non-combustibility stuff, the fire regulations varying in different countries. So yeah, you can do a lot with it.
Okay, Janelle wants to know what sort of external cladding materials would you recommend and what would you avoid using?
External cladding materials, such a massive range. I would say I would avoid using material. If I just had to give a bit of a general answer, I would say I personally avoid using non-vapor permeable materials. That's not always possible. So sometimes for cost reasons, you might use, like even in this house, for example, to try and save cost, we used just a colour bond cladding. So it's basically just got a metal skin on the outside, which is not vapor permeable, which is why you have to have the rear ventilation cavity behind it. And things like, I personally, my preference is usually some form of timber cladding, but it can often be expensive in a high durability class, so like a class 1 or a class 2 timber, or because it's, and with no treatment on it, so it's raw and therefore has a very low maintenance over time, or something like Core 10, which has very low maintenance, but again, it's not vapor permeable, so you have to be a bit careful. I personally think fibre cement sheets are a really good material. Environmentally, it has really good qualities, but then what you put on it is going to define it. So if you then paint it, then you have to keep repainting it, and that becomes a bit of a challenge. So cladding is always a big challenge for any designer specifier to get right, and it's pretty much, it's a key decision from a budget point of view. Unfortunately, there's no kind of easy answer, and it depends a little bit on your environmental principles and how far you want to push them, your budget, your builder, what they have skills in. Obviously, yeah, timber's quite labour intensive, but if you're an owner builder, then why wouldn't you use a good quality timber and take the time to put it on? Yeah, that would be my best answer in a short one.
Okay, Kim's back again. We've got the interior finish on the walls is paint. Are the junctions between the timber components in each CLT panel expressed through the paint? I think he's assuming that the panels are pre-painted.
Even if they were pre-painted, or in this case they're painted afterwards, you would still see the CLT joint, and that's because there's like a chamfer on the edge of each panel where they meet. So even though the joints are very, very tight, there's no sort of obvious cracks or anything. It's just a very tight, straight joint vertically, typically on walls. Then you would still see that as a line because of the two little chamfers either side of it. So there'll almost be like a little shadow line. So that's why probably when you're designing, you take a fair bit of care placing those joints. If you really wanted to, I suppose, if you were putting an opaque paint on, you could stop them up and cover them, but I would be worried about cracking and reappearing of those joints. So yeah, you try to design for them to be expressed.
Okay, Kim again. I think he wants to know what the thermal break is in the triple glazed windows. He's sort of saying, what's the material used in the well-performing non-transmitting?
In the Swiss, there's something called a Swiss spacer, which I don't know the exact type of material. It's some sort of plastic that's a rubber compound in the spaces, and they have little tiny insulation beads inside that. It's almost like a rubber tube that's kind of stiff, and it has these little insulation beads inside it. So if you Google Swiss spacer, it's a kind of a generic product that is used in a lot of Passivhaus certified components, triple glazed IGUs. Yeah, so again, I'm not sure exactly what type of rubber it is. I couldn't tell you. I'm not sure it's even easy to find that out.
Okay, Tony come up with one. We haven't got here yet, but may have soon. What are the issues with termite resistance?
Yeah, very good question. Short answer to that is in Tasmania, we don't have to worry about termites at the moment. Yet, yeah, as the world warms, we could be facing termites in the future. Unfortunately, that's a big area that that my knowledge is lacking in, because we don't have to deal with it. So I just have no idea. But I would suggest that obviously there'd have to be some careful consideration if you're in a termite area. Sorry, I can't be more helpful on that one.
Okay, Mike Cleaver, one of the old Tasmanian Solar Society members who doesn't come to meetings anymore. Over 40 years, he's learned the importance of passive solar-free gain, using the correct proportion of glazing, room location and function, etc. His question is, the German data doesn't take into account the cool temperate zone. So are there any points gained in the pH software? Say concrete slab in your case study. I'm not sure whether you can you might be easier if you look up at the Q&A section yourself and have a look and see what it says.
Essentially, the climate, the cool temperate climate data, all the climate data is taken into consideration in Passivhaus modelling. It's location specific. So for example, when we do the modelling here, it's the Hobart climate data. The elevation is put in for the Ridgeway site. So I would say that is taken into consideration. I think the other things that you talked about, just learning about positioning of rooms and sort of what I would call traditional passive solar good design practices, there's no reason why you can't still do all that stuff and still have a Passivhaus layer on top of that. So you just inform your Passivhaus design concept with that other stuff. But I guess the flexibility in the Passivhaus system is that if you do need to push the envelope, or you have a challenging site, like obviously this site in the case study, it's got a long axis north to south. And so we're able to still get a really good performance, even though the building is relatively deep. It's not a long skinny box facing its long edge to north. So it still performs really well. So that's partly because of the HRV system, partly because of being able to model at the high level of thermal performance. So I guess what I'm saying is the traditional passive solar design constraints are not the same constraints in Passivhaus. Now, you have more flexibility as a designer to use those tools to do other things that you might not have been able to do in a traditional passive solar design. That doesn't mean that all that information that's been gained for, well, hundreds and hundreds of years, actually, if you look back through the record, I think it was Aristotle or someone who did the first passive solar design. You know, all that stuff's still really useful knowledge and still to be thought about. But obviously, all this new thermal modelling and technology and better and better building materials gives us a degree of flexibility that we maybe didn't have in the past. I hope that answers your question, Mike. I think it's an important one to think about.
Okay, Ian is concerned that the service cavity takes up the whole floor in between the two floors, and it seems a waste of volume.
Yeah, I think it's a fair comment. It's a simple sort of, the reason that it goes all the way around is because everywhere around the perimeter, you have the fixings of the walls to the floor. So essentially you've got about 100 mil high bracket all the way around the perimeter of the building and internal walls. And so you have to lift the floor up above that. But I think if you did the fixings in other ways and were clever, you could probably accommodate service cavities in lots of other ways. So I think that's a freedom each designer would have to mess with the system. I say mess with the system because we tried to do that the first CLT job we did, and it was probably more challenge. The challenge was greater and the benefit didn't really, I don't think it's necessarily paid off. And so we stuck with a more tried and tested route on this one. And I think the sacrifice of volume in this case sort of is okay, it's justified. But I think totally fair comment. Sure, you could optimize that in lots of different ways with creative design solutions.
Mike's come back with another one. He's actually concerned about the thermal mass side of his question. I
honestly didn't understand the thermal mass question in there. Is thermal mass important? Yes, sure it is. Thermally isolated thermal mass, super important. We couldn't have got the performance without it. I'm not really sure what the other aspects of that question were, and maybe I can clarify.
In the meantime, Angela would like to know who supplied your triple glazed skylights.
That was also from Unilux. So yeah, same supplier. Briefly on thermal mass too, just so everybody knows, interestingly, CLT has both thermal mass properties and insulative properties. So your energy software, the PHPP software, will actually take that into account. So you put in the specific heat and the density of the product, and so it will take that into account. So it's not, obviously it's not as good a thermal mass as, you know, water or steel or concrete or phase change material or something, but it still has an impact that is not, it's not a negligible impact. It will add to the comfort and performance of the building.
A couple of questions here about windows. Are there operable windows on the upper level? And from the same person, that the windows are a bit deeper than the insulation layer. If you could do it again, would you put the windows in the same place in the wall section?
Two good questions. First one, yes, there are operable windows all over the upper level that provide cross ventilation. So in the master bedroom, for example, there's windows on both the eastern and the southern side, which are operable. And yeah, all through, I think even the walk-in wardrobe has an operable window. So there's operable windows everywhere. I think that's really important. It was a very considered decision to put the windows on the inside with that renovation profile. So they just completely finished. I think it was a really good detail and it worked really well in this house. The very small sacrifice you get from being out of step with the insulation layer in this case was worth it. I think this is a classic example, or a very good example, of what we were talking about earlier, that if this was in a very, very cold climate, a super extreme European alpine climate where you're going to have like 10 inches of snow on the ground, you probably have to factor in something like over insulation of the window frames from the outside that a lot of European passive houses have, which may increase the overall efficiency of the house by 5%, maybe even a bit more. And in this case, because the climate is a lot more moderate, it was a negligible impact. In other words, we've still achieved the Passivhaus standard despite that detail. But it's a good pickup that maybe wouldn't be obvious that typically you would want your triple glazing or your double glazing to be in the same line as the insulation plane. And in this case, they're out of step. The windows are inside the CLT line and out of step with the insulation. But a fairly insignificant difference shows up in the modeling. But again, it's about how far do you want to take the details and the trade-off between manual work to finish things which have been automatically finished in this case, and the finish looks really good. So there's kind of a speed and efficiency benefit in this particular system that we used. So I would do this again in a heartbeat because I'm happy with the result. You could probably combine what I'm talking about. You could still over-insulate, and I think Justin to some degree will over-insulate a little bit just when he finishes off the outside. So you've got retracted cladding everywhere to a degree that allows you to do that over-insulating detail to make up for that thermal break. But at the sill, it's always hard to do. So yeah, getting into a little bit of minutia there, but it's a good question.
Kim is asking whether the modelling considers condensation within the construction.
Really good question. No, it doesn't. So you would want, if you're worried at all about, or not that I'm aware of, sorry, I should say, I'm not certified to use the PHPP software, so I don't know the ins and outs of it, but my understanding is you need to use something like Woofy, which is a specifically a condensation modeling software if you're worried about interstitial condensation. Interstitial condensation, it's going to have varying degree of risk depending on whether you've got a vapor permeable construction, which in this case we do. And also it's going to have, there will be areas of greater risk depending on thickness of insulation, conductivity pathways. There's a fair, fortunately in this build we had Justin O'Connor, who has a lot of expertise because of his pro-climate business, and they've got a lot of knowledge in building scientists working for them and that have heaps of knowledge around condensation in buildings. It's a super complicated area and big learning curve. And I think if you're doing anything where you're at all worried or just not sure, you can engage somebody to use the Woofy software and model your building system. We actually just did that on a very small CLT project. We engaged a consultant, Darren O'Day, to do some Woofy modeling. I'm not sure if you used Woofy, you might have used another software, but specifically to do condensation iterative modeling on a CLT structure in a very different climate to this. Because we were worried, we wanted to test actually, could we just do a structure with CLT only and then a cavity and cladding? Or if we put on a little bit of insulation, what would be the benefit? And we tried all these different versions. But we were worried about interstitial condensation. So we had to look at that carefully. And that modeling was invaluable in that process. So yeah, if in doubt, model it.
Okay, Stan was asking, were the CLT panels installed by tradespeople from Stora Enzo? I think it was all local builders doing that, wasn't it?
Yep, so Justin O'Connor and his crew, it was their first build with CLT, but they're very experienced builders. So it was basic carpentry skills and people that are probably used to moving heavy things around with cranes. It's a pretty generic skill for builders. They pick it up really quickly if they're competent. And Justin and his team are more than competent. I also helped them on site. I'm also a builder, and I had done one CLT house before, so I kind of came along just to try and help where I could. I think there was some value in that, having done it a little bit before and worked with the ratchets and things that pull the panels together and all those little gadgets that kind of help optimize the positioning. Where Justin excelled was that the preparation was outstanding. The leveling of the slab and the lines that all the brackets were set up to were all really, really perfect. So, and then the packing and careful plumbing of the panels and checking everything with a laser was really, really good. So that there were no cumulative errors that sort of built up. I think there was only one panel in the whole job. There's nearly 90 panels, something that needed a very slight bit of modification. Everything else went together millimeter perfect. And I think that one panel actually just had an error in it, which was unusual. So it had a slight, must have moved slightly on the machine. It was miscut, which hardly ever happens. Most of them are millimeter perfect. So, yeah.
Okay, a couple of questions from Cam. Which Australian standard is CLT designed according to? And if it is considered deemed to satisfy according to the BCA, what sort of cost is involved with an engineer certifying the use of it? Is an acceptable construction manual available to use this product system?
Good question. So there is a bunch of resources there. Wood Solutions that I mentioned in my acknowledgements page have a whole lot of resources on mass timber construction. Stuart Enzo themselves have a huge document on it. There's just a whole heap of systems and details. Rothablas have, they're just their product catalogs have heaps of different CLT details and connections. Broadly speaking, I haven't been involved in a deemed to satisfy like multi-residential project in CLT. So obviously if you're going with a deemed to satisfy, your structural system is being certified by the engineer. So obviously they're satisfied because it's timber. It's not some new material like carbon fiber or something. Basically engineers understand the properties of timber. It's a softwood panel, it's cross-laminated, so it's going to perform better than, it'd be similar to say an engineered timber product like LVL or something, just on a mass scale. So I don't think it's overly complicated from the engineering point of view. And in this case, Stuart Enzo has their own software that's fairly easy to use that the engineers gotten familiar with and uses that to plan the spans and things. It's probably not a very good answer to your question. I guess we're not doing anything overly ambitious. It's a two-story house. It's a tried and tested thing for CLT to do that. I think when you're dealing with products that go through other rigorous standards, so they have to comply with the DIN standards in Germany and other European standards and American standards. The Stuart Enzo is a big multinational and exports all over the world. So I guess my point being that these are a really robust tested product that's gone through the rigor of testing everywhere. And at the end of the day, this is not a material that is difficult for engineers to understand or has some unusual, unpredictable properties.
Okay, where'd the one go? Okay, least concerned about the ability of the imported UPVC window frames to withstand the higher UV radiation in Australia. So base summer UV in Germany is 7, in Tasmania it's about 11.
Sorry, would you mind just, I just spaced out a little bit.
That's all right, it's as well past everybody's bedtime.
That's all right.
Basically, the question was about the UPVC rating of the triple glazed windows. They're designed for Germany, whereas the UV rating is about 7, but in Tasmania we have a summer rating of about 11.
It's a good question, except that in this building we had timber built windows, not UPVC. So you're absolutely right that if you imported UPVC windows from Germany and they were exposed to our sun, they'd have a big problem, especially if they weren't a tropical mix, which it means that they have UV stabilizers in them. So if you're using a UPVC window in Australia, you actually need to ask the question: is it a tropical mix? Does it have UV stabilizers in it? Or is it somehow protected on the outside, like with an aluminium cladding or something, which quite a lot of imported European products are. But yeah, in this particular case, there's no UPVC windows in the build, so it wasn't an issue. And obviously timber internally, aluminium, powder-coated aluminium cladding on the exterior. So very high UV stability.
Okay, here's a slightly tricky one. Paul asks, Passivhaus discourages thermal mass, but Natters encourages it. How do you balance the two?
Yeah, that's true that NatHERS encourages thermal mass, and to be honest, if we make it over the 6-star minimum, which we almost always do, most of our buildings would be like 9 stars or something. We don't really worry too much about the NatHERS modelling. We'd be worried more about the PHPP modelling, because that's a real life certified situation where you're looking at not just modeling something, but then verifying it with your blower door test and all the other things. So if PHPP said we could get away with less mass, I would trust it. We're just putting our faith in the science there, I guess. I think there's so many limitations with the CHNF engine, which underpins the 3 different approved NatHERS rating tools, of which Accurate is one of them. That CHNF engine that was developed by the CSIRO, while it's been tested and verified in lots of different circumstances, it still has basic inputs that are fixed. To give you an example, the air change rate in a NatHERS rating tool, specifically in Accurate, is fixed at 5 air changes per hour. So that's a very leaky building. And you're not able to go in and change it because it's in the engine, it's built in. And so if you actually then build a building that's got an air tightness of 0.17 like this building has, which is something, if we do something, 5 air changes divided by 0.17, that's 29 times more airtight than what's specified in the Accurate software. So if you actually put in 0.17 into the Accurate software, if you were able to enter it, verified by the blower door testing consultant, you'd have a much higher star rating. So you can't rely on what NatHERS says simply because it recommends something. It's more like a general trend towards 9 stars. But let's say you get a 9-star rating. And then Justin O'Connor builds it. I would guarantee you right now that it would be better than 9 stars when you actually verified and measured it. But if Joe Blow, the builder who's never done a passive house, doesn't know anything about it, builds it, you could end up with a 6-star building, but it's got a 9-star rating, but it will perform as a 6-star building because it doesn't have any air tightness, it's got gaps in the insulation, it's got thermal bridges everywhere, it just has no idea. So a NatHERS rating is only as good as the piece of paper it's printed on. It really doesn't have that much value, whereas a passive house certification requires thousands of photographs with rulers shown in the photographs and certificates that the right insulation was put in the right place. They check every detail. The blower door test certificate has to be, signed off by an approved passive house qualified blower door tester. There's all kinds of checks and balances that you don't have in the NatHERS system. So I guess my point would be, if I had to put my money on a certification system, I would say PHPP or Passive House and certification well exceeds a NatHERS star rating. Now, what I'm advocating for, and it's kind of preempted in that initial poll, is that Australia needs to push for much higher regulatory standards and that we should be doing mandatory testing. We should be, in my opinion, we should do mandatory blower door tests on all new buildings, all renovations. And we should have standards that you have to achieve. We should do thermal imaging inspections at the same time. This should be mandatory. They're not big costs and they're huge savings and guarantees of quality to the building owner. You don't get what you pay for with a star rating. You just get, it's a gold star. It's like, here's a merit badge, but you don't know if you've actually earned it or not. So that was a little bit of a rant, but I think it's important to know the difference between those two things and what you're getting.
A couple of other modelling questions. Mike Cleaver's back again. How many points did you achieve using a slab in the project?
Couldn't tell you, Mike. I wish I could. I don't know. We didn't ever do a model without a slab, so I couldn't tell you if we sort of got some huge benefit from adding it versus not having it. The site was relatively flat and suited a slab on ground. I guess my personal bias, if you like, is that I believe in thermal mass, and I like the resilience of a concrete finish. It's also nice just aesthetically to break up all of that timber. You know, but that, like I said, that's a personal bias. Like if the modelling software had said it would be just as good with a timber floor, I'd be believing the modelling software. And not just the modelling software. I think I put a lot of faith in that, but I also put a lot of faith in the experience you have living in these types of buildings. I've lived in my own place for 2 years and I've learned things about thermal mass that has positives and negatives. So on the ground floor of our house where we don't get enough sun, the thermal mass works against us. In winter, it's colder on the bottom floor, but on a really, really hot day, if I go down to the bottom floor, it's nice and cool without any air conditioning. So there's pros and cons, have to consider everything. Design is really complicated. These modeling tools give us just an extra window of insight that we probably didn't have before them, that's quite useful to use as a design tool. That requires us to be more interactive with our consultants during the design phase, or learn how to use them ourselves. And like Torquil is also a designer, so when he designs, he puts his designs into PHPP and he plays with different variations and tweaks it as he goes. So he's getting a live feedback from this clever software. Yeah, again, that's kind of how I feel about thermal mass equation.
Okay, well, Neil asks, is the PHPP modelling easy to navigate for a novice? And that'd be a shock if anything was easy to navigate for a novice.
I don't know that it is. It's a pretty detailed, it's in an Excel spreadsheet. I think there's ways to do SketchUp plugins where you can make a basic skin model of the building to get the geometry and import that in to PHPP. I think I would consider myself a novice in PHPP by big time, and I reckon it'd be really difficult to use, in the sense that if you inputted just a few figures incorrectly, you could really throw the whole thing off. So I think I would have a hard time relying on my own skills if I was doing it the first time, and that's why they do whole training courses through. So if you go to the Australian Passivhaus Association, they arrange courses. I think they're like a couple of weeks long, maybe a week long. So they're pretty intensive anyway to learn PHPP and get certified in it. And then even after that, you'd be needing experience of doing quite a few jobs. So yeah, I think there's some challenges there.
Okay, and for lucky last, how much timber by volume for the manufacturing of CLT for your house? That could be a tricky one to work out. How much timber compared to a traditional timber frame house with a non-timber interior?
A really good question. When you order CLT, you actually, when you get the quote, it's usually a volumetric total that they give you at the end. I don't have it in front of me, but I'd be able to work out pretty quickly what the volumetric total of timber was. It wasn't an enormous amount in this. I think it's 20 or 30 cubes, something like that. And then you could probably work out an average for a stud frame and how much more that would be. Obviously, there's a lot more timber in a CLT house than a stud frame house. But yeah.
Okay, we have made it to the end of the questions. So thank you very much, Stuart. That was a marathon effort.
Thanks, Anne.
We've still got 108 people listening. So.
Well done